Good morning. Welcome to this talk about the future of hydraulic modeling into the 21st century. My name is Hubert CHANSON, and I've been an academic at the University of Queensland for 32 years. A summary of this talk is here, starting right from the beginning that as hydraulic engineers, we are dealing with the science of water in motion and its interaction with its surroundings, including sediments, atmosphere, and aquatic life and flora. We are also dealing with a very broad range of engineering scales, both time and length scales, and thus we need modeling techniques to predict the characteristic of full-scale water system performances during design, during construction, during operation, and possibly after failure, as is the case in the bottom photograph, a physical model of the Paradise Dam after a major accident in downstream of the steaming basin. Hydraulic modeling is an expression which in fact encompasses several different techniques. The oldest and possibly better known type of hydraulic modeling is using geometrically scaled models. It is physical modeling, which were likely used in the antiquity by Sumerians, Egyptians, and Romans. Also, modern physical modeling derived in part from the works of Chézy, Reich, and Bazin. That is, it is based upon the fundamental concept of dimensionalities and geometric, kinematic, and dynamic similarities. With any physical model, the extrapolation of the results to full scale will be affected with scale effect with any physical model. And our role as hydraulic engineer will be to minimize scale effects. And there are some well-known principles. And in some situations, theoretical consideration may enable us to use the standard scale model at the bottom photograph, or using different fluid between model and prototype with these aerodynamic studies of this bridge on the far right that have been tested in a hydrodynamic journal. We note a lesser interest for physical modeling in the second half of the 20th century with the development of numerical modeling. And yet, in the last 20 to 30 years, there has been a massive regain of interest in physical modeling, particularly to provide valid detection dataset for numerical, including CFD modeling. A second well-known form of hydraulic modeling is theoretical modeling using analytical solution. For example, using potential flow theory, a very solid theory for the application, for example, of the two-dimensional or three-dimensional flow above a spillway crest. In fact, potential flow theory may be applied to both steady and unsteady flow, 2D or 3D. With laminar flows, there's a classical Poisson flow solution. And even in turbulent flow, the famous log law derived directly from Prandtl mixing length model. In operational hydraulics, well-known theoretical model includes the backwater equation and the Bélanger equation for hydraulic jump, both derived by the Frenchman Jean-Baptiste Bélanger, whose name is on the Eiffel Tower. Other well-known analytical solutions include the Savona equation and the Boussinesq equation, and there have been more recent developments. Another form of hydraulic modeling is numerical modeling, with here two subfamilies: depth average models, including the Savona equation and the Boussinesq equations, and a numerical solution of the Navier-Stokes equation shown here. This approach, called CFD modeling, is far from being trivial, and let me illustrate with a very naive, simplistic approach the difficulty. If we time average a Navier-Stokes equation, we obtain what is called the Reynolds average Navier-Stokes equation. And on the far right, we see the addition of 6 new terms, particularly the Reynolds stress tensor. And thus, since we have no new equation, we need to introduce some form of turbulence model, something sometimes called closure problem or turbulence closure. There are different types of turbulence model, from much simpler to very complicated, but importantly, the selection of the turbulence model must be closely related to the turbulence topology. Of course, we can avoid the use of a turbulence model if we use direct numerical simulation. But to date, DNS is limited to Reynolds number of about 10 to the 5. They are far below the Reynolds number observed in prototype hydraulic structures, 10 to the 7, 10 to the 8, 10 to the 9. And then there are the elephants in the room, the field data. On one hand, field data are costly, very dangerous, sometimes nearly impossible to achieve during rapid deployments. The top photograph on the left shows a situation where I tried to access a dam to see it at the peak of the flood. We drove 450 kilometers on 30 kilometers to the side. The road was underwater. Another example is this particular site that I visited at the end of November last year. And yet at the peak of the flood 2 weeks later, there were 3 meters of water on the road, as you can see on the small photograph, and I couldn't come. We need also, with any data, any field data, ask some question about the quality and quantity. What, how, when, where? What type of data? Who collected the data? How were the data collected? Where were they collected? But ultimately, field data are uppermost important because nature is the final jury. And then I would like to illustrate another form of modeling. Hybrid modeling, combining physical and numerical modeling, with an example on the top right of a small fish swimming upstream of a triangular buffer in a near full-scale box culvert barrel. We find here in this physical experiment that contrary to the traditional understanding, this small fish is swimming upstream of the buffer. And this is explained in the bottom photograph by looking at the CFD modeling with the blue curve showing the low velocity zone. Basically, this small fish is swimming in a low velocity zone corresponding to a stagnation region with low turbulence. With hybrid modeling, physical numerical modeling may be either disadvantaged or using CFD modeling. Generally, hybrid modeling always gives an impression of robustness to people who are non-expert, because people think, oh, they are doing physical modeling and numerical modeling, it must be good, even if it's not always true. But for the expert, the combined use of physical and numerical modeling can bring very high level of interactions, as was done in the development of design guidelines for fish-friendly culverts that use 3.5 years on physical modeling combined with 2.5 years of CFD modeling. And the outcomes would not have been possible by using either physical modeling only or numerical modeling only. I've been involved in a number of hybrid modeling on hydraulic jump with colleagues from the University of Bordeaux, on drop shaft with colleagues from the University of California, Davis, on negative surge in open channel, and in fish-friendly box culverts. 2 further products have been the physical modeling of positive surge, with the top video here illustrating a positive surge propagating upstream in a 0.7 meter wide, 19 meter long flume. Such a modeling has been done quite a while ago in France, focusing on the fluid surface characteristics. But more recently, it has been undertaken with some colleagues from the University of Bordeaux, Professor Lubin and Dr. Lang, which have provided very successful results in terms of the ondular and breaking bar flow field, transient flow field. Although in the line, we still have some issue in terms of computational time on multi-phase flow characteristics. And indeed, if you look on the top video that is replayed, you can see also white water suggesting a relatively strong entraînement, but it's much larger entraînement than in the observed physically. Another project, and it's an ongoing project, is a series of fiction with a colleague of mine, Professor Fabien Bombardier, who has done some very nice CFD modeling on self-spillway. And the work has been very successful in the non-aerated flow region, with recent successful outcome in the inception region, but there remains some issue in relation to the air water flow region, especially in terms of the numerical model. Altogether, we cannot ignore the cost associated on the investment associated with hybrid modeling in terms of infrastructure, computational time, but also human resources. Importantly, one needs to be mindful that the validation of numerical modeling using physical model data will be subjected to the same scale effect as the physical data. In other words, validation with physical model is not valid for a true relation to full-scale prototype without the same scale effect as the physical model data. And then there is hybrid modeling Mark II, that is combining physical laboratory data on field measurement, something that we have developed at the University of Queensland. Potentially, we could have this framework with field data on the left, which show on the bottom left the contour map of the time average surface velocity component in the area highlighted in yellow on the top left photograph, and on the right the physical data obtained in laboratory. And of course, the key point is how does the two compare together. And using a Frost similitude, we can see here the surface velocity data in the developing flow region as a function of the dimensionless elevation, with ideal field flow theory in red, laboratory data with Peter tube with cross, on field observation in green and blue. An astonishing. This approach of hybrid modeling Mark II will require a geometric similarity based upon an undistorted Frost scaling and working with high Reynolds number in the model. Ideally, the instrumentation should include some overlap between the two techniques, for example, optical technique in the field and in laboratory, as illustrated on this video, and more advanced instrumentation in laboratory whenever possible. Importantly, the flow conditions are typically limited or restricted by the possible field data observation. And you remember this video where I told you that I could not observe the flow at the peak of the flood because the road was underwater. So let's talk for a few minutes about optical technique in hydraulic engineering. Optical techniques such as flow visualization have been used for centuries. And even over the past 2 or 3 centuries, some of this optical technique were used for more than qualitative data, but also quantitative observations. In the last 40 years, there have been some velocity measurement developed from continuous photographic or cinematographic records. And of course, I will exclude here in this talk laser-based optical technique LDR-PAV, which typically are most often not applicable in the field. I'm talking about LSPIV, LSPTV, optical flow, and infrared quantitative imagery asymmetry. And at the University of Queensland, we have used LSPTV on optical flow, and I will comment more specifically about optical flow. An unusual experience at the University of Queensland has been to apply this optical flow in 3 different ways. Side view in laboratory as shown on the bottom left photograph, top view in laboratory as shown by the sketch on the top right, and in the field. For those who are not familiar, the optical flow is a branch of computer vision that is used to detect the gradient of brightness intensity as they are convected in the field of vision of the camera. Importantly, the approach requires some good lighting conditions and typically some form of particles that reflect the light. It could be microbubble, it could be a water packet, it could be surface debris or surface roughness. Tracking technique may be both Eulerian or Lagrangian, and ultimately under ideal condition, we can obtain a large amount of instantaneous data, including the instantaneous turbulent Reynolds stress tensor maps. That technique has been applied to 2 field datasets, the Hinsdam step spillway and the Chinchilla minimum wave. Initially, the focus was to gain more information on the air-water surface flow field. It has not always been possible. We'll come out shortly. We need also some field data set, and there were some opportunities in Queensland over the past 12 years. Both structures, by the way, are large dams. In each case, the video records were collected with SLR cameras using a relatively slow frame rate, 30 to 60 frames per second, but very sensitive camera sensor in HD resolution. A typical example here is a contour map of the longitudinal of the Tamil village longitudinal surface velocity measured parallel to the inverse, showing in particular area of high velocity at a data set on the 24th of March 2021, with the corresponding contour map of the standard deviation of the longitudinal surface velocity, showing region of high velocity fluctuations. For this particular application, the Higgs dam, we get great level of detail in the non-aerial flow region, but very poor data in the air water, white water region. At the Chinchilla Weir, surface velocity are shown here in the middle of a bay at the blue dataset, which are compared with the ideal fluid theory in green on backwater calculation in red. Here, we get some fascinating detail on the air-water flow region, but very poor data in the non-aerated flow region because of surface glare. One of the challenges with this type of approach is, of course, the absence of independent validation data sets. And here, hybrid validation was used to validate the field dataset against ideal fluid flow theory or backwater equation and, whenever possible, fraud-scaled laboratory data, either using Prandtl pitot tube or phase detection probe. An example in terms of the surface velocity in the non-aerial flow region is shown on the left. On the right, we show a similar graph again in dimensionless form of the longitudinal turbulence intensity, with field data being the vertical colored line, the asterisk being dual-tip phase detection probe, on the black line, thick and thin, being optical flow using two different lenses. What did we learn from the field? Access is uppermost important, physical access and optical access. We need to have a steady viewpoint, typically a very heavy tripod on a reinforced concrete platform. We have zero control of the atmospheric condition, and we always use high quality professional prime lenses. But we need to remember that at the end, we always need also good luck. So if I try to reflect on the experience at the University of Queensland of using an optical technique in three different ways: laboratory, side view, laboratory, top view, on field observation, one of the key challenges is always the light. In laboratory, we need a lot of light, and it's not obvious to get it right. In laboratory, we have zero control. Light, or where is the light, as says the poet. Second key challenge is validation. In laboratory, we may use some data sets such as a Prandtl pitot tube or dual-tip phase detection probe for validation, but one needs to be mindful that some of the optical flow techniques have a very large number of optical flow parameters that need to be calibrated. And at the University of Queensland, we tend to use some older technique because of the lesser number of parameters to calibrate. In laboratory, in the field, there is an inexistence of independent validation data tests, and we rely upon a hybrid validation. Finally, the third challenge are the resource requirement both in laboratory and in the field, and we need, of course, a lot of enthusiasm. So, what are the main key takeaways? Hydraulic structure and flood are nothing new, but floods do exist. We are dealing often with an aging infrastructure that need to serve safely a growing population, and we have an inexperienced workforce too often. Thus, we need some hydraulic modeling techniques, physical modeling, theoretical modeling, numerical modeling, field observation, But I see the future with a greater use of hybrid modeling. Mark 1, physical and numerical modeling. Mark 2, field and physical modeling. And potentially we can envisage Mark 3, field measurement, physical modeling, numerical modeling. Also, the investment here will be enormous. How about optical technique? They are fascinating because nature is a final jury. If I reflect of our experience to date, I would see an optical technique as one more metrology, not the ultimate metrology. For those who are interested, here are a few slides of relevant bibliography. Thank you.